Our topic, as given to me, was FPGAs for machine learning. We'll talk a little about FPGAs for deep learning. So my name is Jim Moawad with Intel's Network and Custom Logic Group. I'm a technical solution specialist. I've been working in the field of FPGAs for a long time. I'm focused on using FPGAs for compute acceleration. With me today is also Greg Nash. He's a system architect in our Government, Aerospace, and Military Business Unit. And so the two of us will go through a little bit about what Intel has to offer for machine learning and specifically deep learning. And we'll get into how FPGAs might fit in that space a little bit. So this is an agenda we've got for this session. We've got a big time slot here. We'll have plenty of time to talk through some of these things. And I think we'll go through a lot of topics at a fairly high level and then jump a little bit deeper with some things. So first we'll start by talking about Intel as a whole and how Intel has solutions that are geared towards helping with AI and machine learning. And then we'll get into what Intel has done to help with accelerating deep learning with a toolkit that we call OpenVINO. So I'll introduce OpenVINO to you guys if you aren't already familiar. Then we'll get into deep learning acceleration specifically. OpenVINO is a toolkit that is geared towards accelerating with a wide variety of hardware. We'll talk a little bit about FPGA specifically. And Greg will help walk us through a little bit of how that FPGA plugin works. We call that our deep learning acceleration suite, and how we execute with that within the OpenVINO framework. And then we'll conclude with a little bit about our newly announced FPGA family, Agilex, and then an initiative at Intel called One API. So that's our plan for this session. All right. So I guess before we jump into it, I'm curious, how many folks here have at least heard of FPGAs? Yeah, so as I would expect, I think most hands are going up. But then my follow-up question to that is, how many of you have done programming for FPGAs? Okay, I see, maybe 5 hands, 5 or 6 hands. So we'll talk about that gap. That's a pretty common gap, right? That people have heard of FPGAs, familiar with what they could do potentially, but at the same time, there's often not too many people that have actually tried coding up for the FPGA. There's a few languages to do that. Okay. So within the context of machine learning is being found in just about every market, every segment, whether it's farming and agriculture to healthcare to the retail space. I've done a lot of work with retail customers to try and get machine learning more involved in retail a little bit. Just about every market you can think of is looking to do more and more machine learning. And that's driving up the need for compute. So certainly in the area of research and science and high-performance compute, the same trend is happening, and there is more and more need for using high-performance compute systems to do machine learning, and specifically various areas of deep learning. And AI, artificial intelligence, machine learning, it's a pretty big, vast field. So those are terms we hear a lot, and there's a lot involved underneath that umbrella. Whether it's unsupervised learning, trying to take a bunch of data and sort it into various clusters of information, or doing image processing or speech processing or things like that. Okay. And I just mentioned data. Data is what's driving all this. So there is a lot of data out there. A lot of data has been collected in a lot of these different areas that I just showed. And the next question is then, how do we crunch on that data and use that data in a useful way? And deep learning algorithms can help cut through that data and give us some useful results. So Intel is a company that's got a lot of different chip technologies. Historically, Intel for many, many years was a CPU company that made processors, right? It's the big name in processors and nearly all desktop and server type systems. But over the last 5 years or so, Intel has made a lot of investment and acquisitions in other areas as well. So one of the areas is FPGAs, and that's where Greg and I come from. So the heritage there was a company called Altera, and Intel acquired Altera, I don't know, must have been 4 or 5 years ago at this point. And they acquired some other companies as well. And so now Intel has a big portfolio of different hardware architectures that can help with some of these things. And so in addition to CPU, we do have integrated GPUs on many of the processors that exist. Intel has plans for a discrete GPU as well. Intel has a variety of different chips that are geared towards AI, geared towards doing AI in some fashion. We call those matrix architectures. And then the FPGA we categorize as a spatial architecture. FPGAs are a programmable hardware technology. So we've got an array of things that can be arranged however you want. That gives us a spatial architecture that we can connect anything to anything in any manner we'd like. And so from a compute standpoint, in terms of what Intel has to offer, we haven't talked about many of these things just yet, but I'll try to describe a little bit here. The traditional CPUs, Intel has things like the Xeon, which are server class processors. Core I processors are used in other systems as well, desktops and workstations. And those can be used for inference or for training. And then there are accelerators. Intel is designing some accelerators specifically for neural networks. Nirvana is the brand name that's been used. We won't talk really about that today, but just so you're aware that that is something that is being developed by Intel as well. And there's a variant geared towards inference and a variant geared towards training. And then on the right side here are a variety of different accelerators. FPGA. So today we'll be talking about Intel's FPGAs. Specifically, today's FPGAs that exist are a couple families named Aria 10, and Stratix, so Stratix 10. Those are two different families of FPGAs that exist today. Stratix 10 is like the flagship FPGA today. Aria 10 is a pretty high-end FPGA, but it's a tier below that. And then Intel also has other chips, like there was an acquisition from a company called MOVIDIUS. So the MOVIDIUS chips are what we would call a VPU, a vision processing unit. They're geared towards inference for images. And then, as I mentioned a second ago, there are discrete GPUs that are in the works as well. And so we'll talk a little bit about when you have a variety of different compute like this, what makes sense from a hardware standpoint to use. We'll talk a little bit about when it might make sense to use an FPGA, what are those good at, how does that help us in the spectrum. But the idea here is that you've got CPUs as your main workhorse, but there may be places where you'd like to augment that with something else. So in terms of data, right, there's a lot of data that we want to crunch on. So the question is, what do we do with all that data? First things first is if you don't have good data and don't have a good way to manage the data, then of course, garbage in, garbage out. You've got to figure out, do I have good data? How do I get it? How do I pre-process it? How do I massage it? There's the level of I am going to ingest a bunch of data from somewhere, whether it's from sensors or from a data pool that I've got somewhere. That's the first stage, is to figure out where is my data coming from, and is it data that's useful, and what part of the data is the most useful. We're going to store the data somehow. So if it's coming from sensors, right, we typically are collecting all that data somewhere. And then we do need to clean up that data, like I said, make sure we have useful data. And only after we've done all that with the data, then can we properly process it. And so I just wanted to mention that before we jump into computing on the data, that data is a really important aspect. And so sometimes people jump a little bit prematurely into trying to crunch on data, and the data itself hasn't really been studied enough to make sure that it really is good data that will make for useful results. Okay. And with different hardware that exists from a compute standpoint, there's a big variety of different things can be done. And it's a huge field. There's a lot of different things, from k-means algorithms to, different ways of doing clustering, to, whether it's just linear algebra and logistic regression and whatever else. All these different things exist. The main thing I wanted to point out here on this slide is just that there are courses that exist online. Intel has some courses on their website. There's an AI section on the Intel website with courses. So if anyone, myself included, is looking to learn more, there's a lot of useful resources to try and cut through all these different aspects to, machine learning and deep learning. And from an AI software standpoint, Intel has some toolkits to help assist with doing machine learning and deep learning. So on the left side, we have some things specific to machine learning. I personally am not terribly familiar with it, but we have a tool called the Analytics Zoo that can help you deal with data and manage all of that. We have a variety of different libraries, including Python libraries and things that are optimized for Intel architecture. And on the right side, we'll be talking a bit today about OpenVINO Toolkit. OpenVINO Toolkit is geared towards deep learning inference specifically. And it interfaces to a bunch of these frameworks listed below that. TensorFlow, Caffe, those are two pretty popular ones. PyTorch as well, MXNet, right? So we have a toolkit that can allow us to take information from some of these frameworks and bring them in. And the math kernel libraries that exist, I don't know how many are familiar with Intel's math kernel libraries, but those are nice optimized math libraries used quite a bit. There is an extension of that, the MKL-DNN, geared towards deep neural network as well. So something to be aware of is that there are some MKL-DNN libraries that help with doing compute for neural networks. Okay. And so the thought process that Intel has been going to market with and trying to assist the compute community with is that we have a lot of different choices for compute. We are getting to more and more increasingly a heterogeneous compute world. And so there's a variety of different hardware architectures that can exist for doing compute. And so Intel is trying to approach this space with, let's figure out how to make it a little bit simpler for developers and scientists to deploy their AI solutions regardless of what the hardware might be. So we'll talk a little bit about how OpenVINO specifically fits into that a little bit today. Okay. And so from a deep learning standpoint, talked about data. Data is brought into your environment. And then the first stage of that is to bring that into some kind of framework so that you can do training. So in some place, you need to do training so that you can take your model and train it based upon that data, get the weights that you need. And once you have trained model weights, then you can deploy that in some place where you're going to do your inference. And that inference could be, on a high-performance compute system, could be in the cloud somewhere, could be, in a lot of cases, you want to do inference on a device that's going to exist, in a distributed fashion. And in that case, then we want to make sure, if we're going to do inference on a device, that it's a nice and efficient compute, so we aren't, taxing compute resources in a small device that needs to sit out in the field somewhere, or even, a small edge server, as opposed to, being done in a big compute environment. Okay. So our focus today is FPGAs. Before we go into FPGAs, I'm just going to spend a couple minutes on a few of our different chips that Intel has to offer for dealing with AI and what is being done. So from an Intel Xeon standpoint, there was a family that had a code name of Cascade Lake. It was launched earlier this year. And this took the Xeon processor and added some instructions specifically for neural network computations. So we call it, it's branded as DL Boost. What DL Boost is a set of vector neural network instructions, VNNI instructions. And these are instructions that go beyond what can be done with AVX 512 so that you can do some very specific things to really help with neural networks. And this has been extremely helpful in areas like image classification, speech recognition, with language translation. A lot of that is really being accelerated heavily by these extra instructions that were added into the CPU. And so these are some results, right? Taking a baseline of something that might have been done on a CPU a few years back that didn't have any of this, and if we take that, optimize it a little bit, and run it on a CPU, one of these recent Cascade Lake CPUs, we can really see a huge boost in performance of the neural network. Okay. And so similarly, I mentioned these chips that are in the works, Nirvana. And so these will be dedicated chips for neural network processing. So the idea here is this would sit next to your CPU as an offload engine. I won't mention much more, and this is still a technology that's coming up, but it's something that's been announced and will come out later this year. So you may start to see a little bit more info on Nirvana. There are some press articles and things out there. In a similar fashion, FPGA can be used as a way to accelerate compute. It could be used in a fashion that sits right next to a CPU as an offload from the CPU. And so that's one thing that can be done. In addition, you could use an FPGA in an environment where it sits standalone and is the entire compute engine. And that can also be really useful because FPGAs, it's a custom chip. And so we can build up a chip that does not only our neural network computations, but also does other things. Whether it's bringing in the data directly and then computing right on it, or doing things like compression and decompression or other functions right there that can be done with an FPGA as well. So another chip that Intel has is MOVIDIUS, which is a vision processing unit. These are really optimized towards being low power, lightweight engines that can sit in things like a smart camera, surveillance, in drones, and they're highly optimized for visual inference and for keeping things as low power as possible. So this is another thing that exists. Intel also has what they call a GNA, the Gaussian Neural Accelerator, and this is used for speech recognition. And so you can see here there's a big variety of different hardware architectures that can be used, and so it's a diverse space with a lot of different chips, each of them geared towards different areas. One of the unique things about FPGA is that it's a generic chip, and we can build what we want into it. So that's what we'll go into more detail in a minute. Okay. And then GPUs are used quite a bit today. It's a pretty popular choice for trying to accelerate training of neural networks. So that's fairly common. And just to round out the story, another acquisition by Intel was a company called Mobileye. They're really geared towards doing things for the automotive market and autonomous driving. So yet another highly specialized chip. Okay. So moving away from different chips that Intel has to offer into the software side of things, when it gets to deep learning software, there's a big variety of software frameworks that exist out there for doing deep learning, and usually it's on the idea of how do I map my graph, how do I train it up, how do I deal with all that. I mentioned some of these names a minute ago: MXNet, Caffe, TensorFlow. There's also some of the data engines like BigDL from Spark, and so there's all these frameworks where you're typically going to start working with your data. And then there's a wide variety of topologies that exist. a lot of the public topologies that are popular are things like ResNet or MobileNet or VGG. So those frameworks and the topologies, right, you work within a topology on your framework, and you may use a standard topology that exists out in the public domain, or you may modify that and tweak it up for your needs. But those two pieces are needed to create your deep learning environment. And then what Intel does is try to work so that we can interface with any of those frameworks. And we have various ways of optimizing things depending on your topology. And then we've got various libraries, like I mentioned, the MKL, DNN. So when it comes to GPUs and OpenCL, we have a CL-DNN library as well. So there are libraries to help and make sure that various functions your network needs to do are optimized. Okay. So just to clarify a little bit on frameworks, I've mentioned some of these frameworks a few times, but there is a new, relatively new consortium or standard that's emerging a little bit, ONNX. So ONNX is nice because instead of having 5 different frameworks, each with their own output, ONNX is an attempt to standardize a little bit. We'll see how that plays out. But today we at Intel, we have our tools. They talk and they can read in information from TensorFlow or MXNet or Caffe, but also from ONNX. ONNX gives us a path in from things like PyTorch. PyTorch, I'm seeing more and more use of PyTorch. So that's just something that is useful. And as things emerge, if things standardize underneath ONNX, that'll be a good thing. We'll see how that, what happens there. So 2 big categories of neural networks are, convolutional neural networks, where you have a convolution layer, and then you have, you may have pooling layers or fully connected layers, and these are where we have, each of the layers is comprised of a set of neurons, and the neurons have a certain weight associated with them, and usually an activation function, and how those weights are assigned is based on your data, right? So we train on a bunch of data, and based on the data that's come in, we will classify and or we'll adjust what weights make the most sense, right? So this means that you need to have data that is tagged and labeled so that you can train your network, so that you can get some weights for your convolutional neural network out of it. Another category is recurrent neural networks. So LSTMs or long short-term memory networks. Things like that as well. Okay. And then these get mapped into different spaces. So different kinds of tasks. These are probably 3 of the big ones, right? Image recognition or text processing or speech recognition. They map into a space of, is it a convolutional neural network? Is it a recurrent neural network? Or maybe somewhere in between. And image recognition typically falls into the CNN camp, where something like text processing usually falls into the RNN camp. So then when it comes to different topologies for deep learning, there is a variety of topologies, and you guys will have access to these slides, so you can look at this table and reference it a little bit. But we're going to talk a little bit about FPGAs, and we haven't necessarily explored everything that FPGAs are good at Intel yet. But today we are doing a lot of work with FPGAs for CNNs. So we are doing using convolutional neural networks in FPGAs to do tasks like image processing, image recognition. That's a pretty common use case. LSTMs work pretty well within FPGAs. So we do have implementations where we're doing LSTMs, and we've built up the LSTM engine inside an FPGA. But given that an FPGA is a flexible open architecture, right, there's certainly other areas that might work very well within an FPGA. And so the places that make sense, we saw a bunch of different dedicated chips that do various things. If there's a dedicated chip that does what you want, then typically that dedicated chip will do that task really well. But if there's an area where there isn't a dedicated chip that does what you want very well, this is an area where it's worthwhile to look at an FPGA. Then you can build up an engine that does exactly the type of thing you need in a very efficient manner. So that's where we are looking to FPGAs, is to fill the gaps and find adjustable architectures to meet the needs of something that doesn't exist in some of these standard off-the-shelf accelerator chips. Okay. So as we look at different networks that exist, I mentioned some of these public domain standard networks that exist. There's two charts here. So the chart on the left shows the accuracy of the network. So if we feed it a bunch of data and give it a labeled data set and then test our labeled data set, what kind of accuracy are we going to get? And these various networks have a level of accuracy shown here. And the chart on the right here shows the compute requirements. As you go towards the right here, it's a heavier compute environment. So something to note here is that, sometimes just because we're doing more compute doesn't necessarily mean we're getting better accuracy. So it is nice to be able to find a network that can give you good accuracy and yet not have such a heavy compute requirement. So just something to think about. All right, so that kind of gets us through our first section, sort of an introductory section on what is Intel doing in the area of AI and machine learning. So now we'll get into a little bit more of the meat of our content here. And so I'm going to talk about a specific toolkit, OpenVINO toolkit. I guess again I'll ask, has anyone heard of OpenVINO? Yeah, we got just one hand maybe. Okay. So it is a relatively new toolkit from Intel. We'll talk a little bit about what it is, where it fits in, what we've done, why we've done it, and get into how the FPGA piece of it works, because it's a toolkit that works for a variety of different hardware architectures, and talk about that a little bit more. So feel free to interrupt me and ask questions. I don't mind being interrupted at all. So we'll get into the Intel OpenVINO toolkit and how we can use that to accelerate deep learning inference. So I mentioned already training and inference. So there is the training side of deep learning where I take my data, I crunch on that data, I try to train up a network to get weights that work well. Then the next stage is to then take the results of that trained network and run it, run inference on it. So the example up here, human bicycle strawberry, right? I give it a bunch of pictures of labeled data. If I had a network that I'm trying to train to be able to differentiate and find humans, bicycles, and strawberries, I give it lots of pictures with humans, bicycles, and strawberries. They're all labeled. I train the network. Then when I run inference on it, I give it a picture, and it can say, okay, based on the weights that I came up with from training on all that data, the thing I'm seeing now, has the properties of a bicycle. That's a bicycle with X% confidence. Okay. So the OpenVINO toolkit is really a toolkit that's geared towards the inference side of that. And it's a toolkit that, it's a whole suite of tools, really. And there's a lot of pieces to this. It includes things like OpenCV. So OpenCV, by the way, was a standard that Intel had come up with many years ago and then released and spun out into the open source community. And there was a separate group managing that. Actually, it's now back under this standard is back under the management of Intel. But OpenCV, right, is a nice computer vision library of various functions to massage your video feeds going in and out. So that is part of OpenVINO. OpenCL as well is used quite a bit by OpenVINO. OpenVX doesn't seem to have as much traction or adoption, but that's underneath the OpenVINO umbrella. So a lot of these traditional computer vision tools are part of the OpenVINO umbrella. And then on the left side here, we have various deep learning frameworks. And so what OpenVINO has done is be able to interface and take output from all of these standard deep learning frameworks and target various accelerators, all those ones that we had mentioned a minute ago, or many of them anyway. Okay. And by the way, OpenVINO is a cute sounding name, but it's actually an acronym. So it's open because it's an open standard, it's open source, it's published, at least a good majority of it. And then the VINO is Visual Inference and Neural Network Optimization. Okay, so today we're talking about FPGAs a little bit, and that falls into the portion of OpenVINO that is the Deep Learning Deployment Toolkit. And so this is two pieces that work together. One is the model optimizer. So that portion of it, at a high level, is a Python-based tool. It takes the output of any of the deep learning frameworks and converts them into a standard form, a standard representation. We call it the intermediate representation, IR. So it's a XML text file, but it's a standard format regardless of which framework you're coming out of. So we have a way to convert from any of these standard frameworks, and we'll turn it into an IR file. So that way we have one single representation. And while it's doing that, it also does a little bit of optimization in terms of looking and converting things so that they are a little bit more optimized for inference compute. And then that's fed into the inference engine. So what is the inference engine? The inference engine is an API, a tool that will take the model that we just passed through from Model Optimizer, and it will allow you to run it in a variety of different hardwares. So we have a plugin for just running straight on a CPU. Okay? And the inference engine for CPU will take your model and make sure you have a nice optimized set of code for the CPU. Similarly, we have a plugin to be able to run on GPU, and what it does, it creates OpenCL code for a GPU. And then from an FPGA standpoint, there is a plugin. That plugin consists of something we call the Deep Learning Acceleration Suite, or sometimes we call it DLA. We use that acronym a little bit when we're within Intel when we're talking about the FPGA piece. But what that is it's a really slick thing. When I asked you guys earlier, how many of you have coded for FPGAs? Only a few hands went up, yet we had a room full of people that know what FPGA is. So this plugin is extremely useful for folks that want to use FPGAs, but maybe haven't gotten into coding for the FPGA, and maybe don't have the time or the investment to learn how to do all that and go through all the various tasks of writing in a language like Verilog or VHDL or even OpenCL for FPGAs and learning how to use all the compiler tools. It takes care of really just about all that for you and creates an FPGA project by using OpenCL and gives you an FPGA image, an FPGA compilation that you can then use and use your FPGA that is geared towards what you've done. Okay. All right, so when we get back to AI software and the big picture, talking about bringing in data and all that and preparing data and everything, when you look in industry at and even in industry and the open source communities that exist, there is a huge amount of tools that exist for dealing with all of this, and all of these tools are things that get used. So question is, where does OpenVINO fit into this? So OpenVINO fits into this piece of it, right? Taking the results of your model and then dealing with the deploying and the inference portion of that. So this is where we fit into the big picture. Something just useful to point out is I mentioned OpenVINO. The open is, there's an open source version of the toolkit. So in addition to an open source version of the toolkit, there's also the Intel distribution of the OpenVINO toolkit. So what are the differences between these two things? So basically we've taken our entire toolkit and we've open sourced a good majority of it. There are a few pieces that we haven't open sourced, basically because we consider those some of our secret sauce and intellectual property and bread and butter. But for example, like the FPGA plugin itself has not been open sourced. So you would need to use the Intel distribution for that. Now, there's no cost to the Intel distribution. It's free software that anyone can use. But just wanted to point out that there is a difference between the open source version, which you'll find source code for, versus the Intel distribution, which is free but doesn't really have a cost. So it's readily downloadable. So the OpenVINO toolkit, in addition to being a tool that can do this model optimization and an inference engine, also shipping with it are a bunch of samples to help get you going. These are things that are full projects to show you how to do things like age and gender recognition. So what we've done is we've pre-trained a model to do that task and given you the results of that pre-trained model so you can give it a try. And so right out of the box, you can go and you can start running inference on a bunch of images, and it will do age and gender detection on that. Or head pose estimation, or text detection, recognition. This is a list of examples that exist. These are all up in something we call a model zoo. They're open source examples that exist, so you can take them and use them as a starting point, and use these samples to get going with a project. So in terms of deep learning acceleration with FPGA, one thing to note is, inference requirements vary a lot. What kind of performance do I need? What kind of power envelope do I have? What kind of batch sizes am I going to be sending in? What kind of precision do I want to run with? All of these different aspects are different requirements that you might have for when you do your inference. And given that there's a lot of different requirements here, there's no one-size-fits-all solution. So this is where it can be nice to have an FPGA. We can build a custom engine that can do whatever is suited well to the network you need. And so I think most of you raised your hand when I asked what an FPGA is. You said you know what an FPGA is. So just a quick refresher, what's in FPGAs? Well, we've got a bunch of configurable logic along with an array of DSP blocks that can do multiply and memory blocks. And so that stuff is good for matrix multiplication, and that's exactly what we need in terms of neural networks. So that's the motivation for taking this chip that's customizable, and it works well for especially CNNs because we've got an engine that can really do matrix multiply well. Yeah, you got a question?
Yeah. When would you use an FPGA as opposed to GPUs?
That's a good question, right? When can we use an FPGA as opposed to a GPU? And so GPUs are definitely a workhorse that have been used for deep learning networks quite a bit. FPGAs work in some of the cases where you maybe have large image sizes. I've got a lead-in. Your question's almost a lead-in slide to something I was going to show in a minute, so we'll touch on that. Maybe we might as well jump there now. But things like large image sizes work well in FPGA. We've got a lot of memory buffers, so we can handle big image sizes, big models. We tend to be able to do those things without running out of memory. In addition, latency is a big factor. FPGAs, we can do things with very deterministic hardware that are highly pipelined. It's all done in hardware without a sequential engine. So the latency you get for your inference can be really low. So there's applications out there that need to do the inference and have a really low latency to them. So that is an area where FPGAs excel. So there's a few pieces like that. Also, there's some environments that just are harsh environments. FPGAs have been used in harsh environments a lot, whether it's running 24/7, 365 for many, many years, being able to run at wide temp ranges. Those are some areas where FPGAs work well that maybe GPUs might not. So again, your question's a good one because there's a lot of places where GPUs work well, but there are definitely places where FPGA also work well. The other thing I was mentioning earlier is FPGAs can be mixed with other things too. So sometimes you want to build a system that's really just a custom hardware system that isn't just CPU plus offload. And that's a place where you can build whatever you want around the engine in an FPGA. So Greg, I don't know if you had something else to add as well.
Yeah, I think my favorite is the fourth bullet point there, which is because of the ease of compilation of GPUs, you've seen a lot of sort of like essentially GPU in the development loop. So we have a lot of networks that run well on GPUs because that's what people have been using. But if you're actually looking at, how do I solve this problem, the ideal solution may not actually fit into a SIMD architecture. By which, and I'll go through the customization flow later, we can support different instruction units and all sorts of different things. So it allows you to actually have more flexibility in the problem or the solution search space to solve the sort of neural networking problem you'd like to solve. And as these continue to evolve, because we're programmable at the gate level, like that picture that Jim showed a while back, there's a really good chance that you'll be able to find a solution that fits well in FPGA.
I was wondering what specifically gives you a large temperature range and what's the trade-off to get that range?
So it's just a matter of trying to build a chip that's a little bit more ruggedized. And FPGAs have had a motivation to do that for a long time because of the end markets that have used FPGAs. So they've been used heavily in telecom and military, and those kinds of customers have demanded, we want a chip that is a little bit wider temp range.
But it's like a material, it's just like a different material or something, but what do you lose by getting that range? Because that's awesome.
I mean, you lose Fmax. And typically how we do it is we're in manufacturing, we're keeping control of the product mix. So you'll have, as die come off the line, some of them inherently are on a different part of the process variation temperature spectrum. So we basically, when we test them, we take the ones that still can run fast at high temperatures and low temperatures, and we bin those out for higher sale prices.
Yeah.
Because they are like, we're going to build 1,000 chips, and 200 of them will work faster and better than the rest. So we support that, and it is because of the embedded heritage of FPGA. We're not, we're a $2 to $3 billion slice of the market for PSG, and to support that, we're looking at this. We call it low volume, high mix applications. So we're set up to support putting the right die into the right application's hands. Just the heritage. We're not. Other competitors are geared towards, I'm going to build this piece, and usually part of that will be consumer culture, and I'm going to ship 100 million of these. And that's great, but you just can't control for these temperature ranges when you do that.
Yeah, and so other chip makers could certainly build chips that are geared towards wider temp range, but we've had a motivation to do it for a long time. And we do build two flavors of all of our chips, right? There is the commercial temp range chip, but every single chip, every single FPGA we ship does have an industrial temp range option. And
it's the same way with the lifespan. We've had a lot of traction in medical industry, just because it takes so long to get through FDA approvals that often by the time you clear your FDA approval, the chip you started designing with is now obsolete. But 8 to 10 years is actually low. Our typical lifespan for a chip is 15 years. So we continue to ship for a long, long time.
Yeah, I was just at a medical customer, and they were just saying, we have some, chip makers that come in and they say 3-year life or 5-year life, and they're like, that just doesn't work for us. it's 3 years by the time we're done with FDA approval and get it into the market. And then we want to build it for another many years. So when we use FPGAs for acceleration, we can get a big boost in improvement. So this chart here is, the details are at the bottom, but it's a specific inference workload. Came out of standard cafe, that's the baseline. When we accelerate with OpenCV, where you can get better performance, it will optimize things. We're still running on the CPU, that's that second column. And then the middle column here is if we just take OpenVINO and optimize for CPU. So you can see here, OpenVINO is doing a bunch of optimization for CPU so that we can get better performance on CPU versus what we would get straight out of our cafe framework. And then this fourth column here is using the integrated iris graphics that's on a lot of the today's Intel processors. So we can get some boost there. But you can see here, if we accelerate and offload things to an FPGA card, we can get a nice boost, many orders of, many times the performance. So we get like an order of magnitude more performance by offloading to an FPGA. Okay. And the three examples here we've got are Google Net, VGG16, SqueezeNet, and it'll vary depending on your network and how well that maps into building an accelerator into the FPGA. But these are pretty typical of a lot of the CNNs. And so FPGAs tend to be very real time. It's a hardware architecture. We've built a custom hardware architecture to do what you want. So that makes it have a very real-time, low latency characteristic to it. And it's real flexible. And while FPGAs, programming for them aren't necessarily easy, within the OpenVINO framework, the fact that we're generating the FPGA image for you makes it a nice, easy way to implement that. So we have made it easy to use. And there are a bunch of public companies that have made announcements that they're using Intel FPGAs for machine learning. Microsoft is probably one of the big names being, using Intel FPGAs. They've been using them for a long time in their cloud infrastructure with Azure and things like that. And so why FPGAs? Well, we can easily build up an architecture where we have a bunch of processing elements. We can put arrays of them in, and make the array as big as we can fill up into a chip. And we can organize them how we want. So rather than have a chip where we've fixed in and locked it down and then made our silicon, here we've got a flexible programmable chip, and we can build up what we want and organize it the way we want. And Greg will talk a bit more about what exactly we're doing there and how that's done in a minute. And that gives us a customizable engine, so we can get a wide variety of different networks out there and customize our performance based on the network that we're bringing in. Okay. And I think with that, I'll move here. Greg's going to talk about this a little bit more, but the other nice thing with FPGAs is we do have the ability to have arbitrary architectures. We can change the bit widths of different elements and layers. What bit width are we using, whether we're using 16-bit floating point or 11-bit floating point or int8 or things like that. There can be things done with weight sharing and all that. So the fact that the FPGA is flexible allows us to adjust our architecture as needed. And then I mentioned that we do get a nice deterministic system latency. And so this can give us a big advantage. And I mentioned some of these family names a minute ago. So ARIA 10 is our workhorse kind of FPGA family. It's used in a lot of different places today. Stratix 10 is the flagship FPGA. At the end, we'll talk a little bit about the next generation FPGAs, Agilex, which is a follow-on to these FPGAs, nice high-end family. But in any of those cases, we get really low latency, and actually, the compute time within the FPGA is really low. And in a lot of cases, a big chunk of the latency is even just getting data to and from the FPGA itself. So that's another nice thing with the FPGAs. Okay. And so for vision and CNNs, the Deep Learning Acceleration Suite is the tool that we have. It's more than a tool. It's a whole engine that generates an FPGA project, an entire FPGA project for you. And it creates the network that does all of the compute for you. And it builds an engine like this, where we have a convolutional PE array connected with a feature map cache, and that has access to local memory that sits alongside the FPGA. And then there's a crossbar switch where we can have various primitive layers coming in, things like a ReLU or a softmax or whatever else we might need can be brought in via this crossbar switch. And so this is the FPGA engine that is generated underneath the OpenVINO toolkit. So again, I'll get past this because
the key thing here,
yeah, go ahead.
Just when Jim talked about the gap between people who knew what FPGAs are and people who use them, is the under software deployment, where we mentioned that there's no FPGA compile. So as part of OpenVINO, we're going to ship a set of images, and I'll get into why we ship a set and not a single one. But this image essentially is a application-specific signal processor on an FPGA, which means that when you go to do inference of different networks, all you're loading is the weights and how to traverse that network, and I'll more on that as well. But you're just reloading that config engine. And the key thing here is that you're having a very software-like development flow, where the compile time from an input network to running on an FPGA is in terms of minutes and not other units of time longer than minutes associated with FPGAs.
Mm-hmm. And so that then brings us to the FPGA flow here when it comes to using OpenVINO is start with a trained model. Then you'll push that through the model optimizer. That will then generate the IR file, and that'll get fed into the inference engine. And that inference engine will be used offline to generate an FPGA image. And then in runtime, you'll run your inference on the FPGA image that was compiled on an FPGA card. So down here, there's a pretty picture of an FPGA card. There are some standard FPGA cards that exist. You can pop them into a PCI Express slot on a CPU, and we can run our inference on that FPGA card. Okay. And so that's effectively the flow here that we just described. And I don't know who here is familiar with OpenCL as a compute language. I guess show of hands. Who's familiar with OpenCL? I'm guessing a good chunk of hands went up, right? So we are generating this FPGA project by generating some OpenCL. So this is all under the hood. You don't have to code in the OpenCL, but just so you're aware, what this suite does is it generates OpenCL code, which is then compiled and turned into an FPGA image, which you can then run on your FPGA card. Okay. And so that is the quick overview of what we're doing in terms of FPGAs. I'm going to hand this over to Greg, who's going to walk us through that FPGA Deep Learning Acceleration Suite, the DLA portion of it, a little bit, and talk about how that works in more detail.
Thanks. All right. So again, I'm Greg. I'm a system architect for government and public sector, so I deal with the HPC space, but I've been doing a lot of signal processing for a while in FPGAs, and most recently came from doing a bunch of this stuff for the autonomous driving space. So definitely ask me any questions as we get going here. I do think this is an interesting audience for the topic of moving deep learning into FPGAs, because I see a lot of the different icons, and no one's got an icon for ImageNet. which is where a whole lot of the sort of the literature revolves around deep learning. And we're seeing a lot more deep learning going into new problem spaces. And I think that having a more flexible sort of canvas to solve that problem is going to, open up new solutions to the existing problems. All right, so I mentioned that we ship we ship precompiled images for the FPGA, and that's to give you a software-like experience. I guess the one thing that we're sort of dancing around is that actually compiling to the FPGA, because we are, really writing down to, programming individual lookup tables and individual routing infrastructure. The solution space for a problem is just huge. It's more akin to ASIC design than it is to compiling for a CPU or GPU, any sort of instruction set architecture. So for some of these narrower problems, we can give you things that are precompiled and thus give you the sort of fast compile experience. But we still support customization, so we're going to talk about how you might customize coming up. The basics of how we do this is we've got this picture we saw before where you've got a processing element array that does convolutions and fully connected layers. We've got a crossbar switch that connects the other pieces of your network. We sort of do this in a ring buffer as shown below here. And we've taken care of a bunch of these things for you. How to parallelize the filters, how to parallelize input depth, how to deal with load match. We've done Winograd transformations in our convolutional layers so that you can do less multiplications. And that's sort of all stuff that's done that you get with this library. So in terms of neural networks, is everyone really familiar with neural networks, or how much time should we spend on the basics? People really familiar? Okay, all right, I'll spend a little more time here. So in general, actually, I came from signal processing. For me, this is like a large adaptive filter. But what we're going to do is we're going to take input features that we want to recognize, and we have a 3D box that computes things that are in this output layer. And we slide this 3D box across the image, and this is essentially picking out shapes. So every layer in this thing, as we repeat this thing, so we'll run through here, and the first layer will be one sort of feature that we're doing, and we repeat this. So in an image classification, each of these layers, let's see if I can point on the screen here, each slice of this box might be curve or corner or straight edge or angled straight edge. And as we convolve through this image, it's saying curved thing here, straight edge thing here. And then this process repeats essentially to get scale. So for us, we're going to take the output blob, make it the input blob, and then we're going to repeat this process. And as you scale through the image, that's going to be essentially identifying more and more complex features in an image. And then again, so much work has gone into image classification and quite a bit into speech classification, and there's a lot of finance work. But I think in general, there's a whole lot of problems that are still yet to be looked at. I've been seeing a lot of sort of combining fields where in computational fluid dynamics, you might have these large grid computations, but you may be able to deal with a coarser grid if the innermost kernel might be a neural network trying to extract these features. And these are all just sort of described in terms of dimensions that aren't really fixed. So all of that can be handled. So this is a picture of the AlexNet graph. This is kind of famous, but it's really old. The reason we're going to talk to it is because it's super simple and it fits on a slide. So AlexNet has got 7 layers. They're sort of color-coded. Up here on what the layers are. So conv is convolutional. This is typically a 3x3, 5x5 sliding window. RailU is rectified linear unit. This is the nonlinear part that's supposed to act neuron-like in terms of scaling things back into 0 to 1. Normalization is just sort of rescaling things inside of a layer. Max pool is when we go from larger sizes to smaller sizes. We usually pick the max of 2 adjacent pixels and return the one that comes out. And then fully connected is typically where we're actually going to assign a value to something. So you look at sets of features and you're going to assign a classification of those things. And because they have these sort of repeated structures as we go through the layers, so we've got 7 different layers on the build. We'll select the first layer here. In the FPGA, we've got this ring buffer that sort of runs around here. So we use a bunch of those different memory elements, usually around half of them, though I'll talk about some trade-offs coming up, to store double buffers. We'll still an input and output buffer, and we'll stream the input data from here through that processing element array where most of the compute is, through your activation layer, which in this case is ReLU for AlexNet, through the normalization layers, and this is all pipeline, so it's all happening in parallel. So we start reading data out, and it just sort of moves in a big pipe and fills up this output buffer. And as this output buffer is filling up, once this input buffer is empty, we move to the next layer. And again, this is only a 7-layer network. Most of these modern networks are 100 layers or 70 layers. That'd make a really busy slide. And we feed through this again. And as we get through this, we'll get to layers where we no longer do the normalization and pool, at which point we just bypass these elements of the FPGA. Things move a little faster. Same with the next layer, next layer. We do kind of a fun thing here with the fully connected layers, and we'll get more into this in the batching. But in the fully connected layers, you have a lot more weights per layer. So there we'll actually reverse the roles of the filter cache and the feature cache and allow that to run at full speed as well. Again, that's kind of transparent to the user. And we do the fully connected layers and eventually produce a weight, which we then send to the CPU to do softmax and classification. So that's what we're doing. How do we parallelize these things? So we've got all these individual processing units. They have their own dedicated filter cache. And these things are arranged in a serial fashion around the chip. So we've got several of these filters running at the same time that we're doing parallel convolutions along these depths. So we stick the sticks into the individual sticks through the 3D space into the individual filter caches. These things pipeline the answers through, do the convolutions, and pass them through to the activation layers. When we do the Winograd transform, this is just a way of trading off multiplies and adds. The key thing when we've got to do a lot of these things in parallel is the adds and the adds and subtracts we need to put on the ends of the Winograd transformation only need to be done in the input and output. Where the multiplies we save, those are all parallelized up. So we get a pretty big bang for the buck by adding, in spatial terms, we add, I think, 6 different adders and subtractors at the beginning and end of these translations, but we save half the multiplies along the way. So again, these are things that we found that rapidly speed things up. As well as in the fully connected layers, again, we've got a lot more weights per pixel. So where we can, and AlexNet would be one where we don't perform well at batch 0, but many of the other modern networks like ResNet and GoogleNet have much fewer fully connected layers. But if we've got a lot of fully connected layers like an AlexNet, what we'll automatically do is we'll batch up a whole bunch of image data, store it in the filter caches, and feed the weights through the feature cache in order to do fully connected layers quickly as well. So again, one of the things that speed up FPGAs is we've got this large amount of distributed memory. So inside of each of these, I'm talking about the filter cache. And the feature cache, the nice thing about doing this in the on-chip memory on the FPGA is it's very quick. It handles random access very well. So when we store this on the chip, we've got 2 cycles in and 2 cycles out of any specific location. And we can adjust the size of this thing in a pre-compiled way. On the filter cache, this is where we use those little bits of memory very near to the DSP blocks. And we've already figured out the prefetching algorithm. So as we're computing one layer, we're prefetching the weights for the next layer, filling up basically a shadow version of the filter cache. And when we switch to the next layer, we just bounce over to the next filter cache in order that, basically, in FPGA, the goal is to never make the data stop. It's sort of like musical chairs. Just got to stop, keep the music from stopping. So using the prefetching, the double buffering on the feature cache and the double buffering on the filter cache, we can achieve this sort of constant movement of data. We mentioned a bit about the flexibility. These are just some of the data types that we've looked at. So when we first started doing this stuff 4 or 5 years ago, The dominant data type was FP32, and honestly, we're really excited about that because we are the only FPGA company shipping dedicated single precision floating point multipliers. Soon the science moved on and said you don't actually need to use all that precision, and we started building block FP16, and that worked well, and then we went down to block FP11. This still works well. Some of the interesting things that are, I think, hard for the folks doing fixed architectures to understand is that we can actually fit more FP11s into a chip than we can fit into 8s, which has to do with some details around our DSP block structure. And then this is actually one of those rare times when there isn't much trade-off, because we actually get more FP11s in a chip than we can get int 8s. And FP11s require less retraining typically than int 8s. Usually no retraining. We just scale FP32 weights into FP11, and things work well. Microsoft has got some really advanced compression algorithms that allow them to get some very good numbers with FP9, and we can fit almost double the FP9s into a chip as we can FP8s. But as FPGA technology keeps moving forward and networks keep moving forward, again, being sort of programmable on this gate level allows us to track those changes. More onto the flexibility. So we ship a lot of different sort of optimized things, and mainly it's because there's popular networks. On the popular networks, we've sort of found the sweet spot for these. So some of them have more elements. So, for example, if you had a network that had a lot of different primitives, we could stick these all in there at the cost of having a smaller PE array. If you have a network that has very few primitives, we can make a very big PE array. And that allows us to sort of we're not fixed. We can build optimized images for every different network, and we have. Another thing is, depending on the ratio of weights and image sizes to convolutional PEs, we can adjust the size of our feature cache in the same way to basically always be building FPGA ASSPs that are sort of suited towards the network. And you can swap these things out in about 100 milliseconds, so it's quite nice. So we have seen that there's this trade-off between having a larger PE array size and a feature set size. And when we plot the speed of different networks, normalized for this, you can see that Alex networked sort of better at one end, Google networked better at another, ResNet was sort of a little more agnostic. But in FPL 19, which is just about, we're publishing a network where we're putting out a tool that'll actually look at your network and tell you what structure of FPGA processor would work best for that network and help you build that. So that's kind of a nice thing. We also sort of, this will be part of the model optimizer as well, but we can build, we can basically splice convolutions together and feature clashes together to give good performance and just reduce the amount of memory needed on chip, which means that you can then get more processing elements and compute things quicker. So I mentioned the precompiled architectures. These are the architectures where we've looked at the network and we found which ASSP structure is optimum to give the best results, and we ship these with the Intel distribution. So again, on the Intel distribution, there is no compiling of FPGAs, just compiling of a network onto the specific architecture you have and running that for good results. The topologies that we're going to support on those primitives, and this is the R1 release. We're on R2. We've added deconvolution, which is really nice, and the segmentic segmentation, and some other things. Yeah, basically this is just showing the flexibility that we're not locked into a single network. Coming up here, we're going to actually start to have a toolkit, and you'll have to talk to an Intel person to get the toolkit, where we can make this thing more customizable. So perhaps in your research, you've got a activation unit that works better than typical ones, or you don't need a ReLU or whatever. What we're going to do is actually we're going to ship some encrypted source for these things. We're going to allow you to replace the processing elements with processing elements of your own. We're going to allow you to replace primitives with primitives of your own. at an OpenCL level. And with our OpenCL, we can actually encapsulate RTL if you've got some stuff that you think is really best expressed in VHDL or Verilog, and basically use that OpenCL framework that we use to build these accelerators. You can basically muck with that at any level you want in order to build your own accelerators for your problems. So we've had this slide a few times, but it's sort of setting up the next section of the presentation. In general, the flow here is you've got trained data, or you've got labeled data at some point. You're going to train a network. You prepare the model to run on an inference engine, and we've got the model optimizer, which we'll talk about soon. And then we've got this inference, which we're going to use that inference engine. These are the two key parts of OpenVINO. These are beginning sort of repeats of the slide we've said, but we've got the model optimizer and the inference engine, which is going to talk to this DLA software API. Typically, this is below what you see, but this is the part that we've coded, and you can customize and use these precompiled architectures. All right, so let's talk about the FPGA suite, the bit streams we ship, the runtime library that we provide. We've got board support packages to support a couple boards, and the tools to diagnose and generate bit streams. All right, so the model optimizer. The model optimizer does what we consider to be technology agnostic optimizations. So it'll convert any of those different input models, depending on whatever language you've run, into our intermediate representation, which we're going to move to ngraph later on. It'll do a bunch of these sort of basically algebraic techniques that reduce the amount of computation necessary, and that's true of any target hardware, CPU, GPU, or FPGA. It'll fold the constants into the data path again. If you're multiplying two numbers, you could multiply by the product of those numbers and save yourself an operation. So it's doing things like that. It also does the quantization, optimizing technologies, and conversion into that full framework. Just a bit about the different data types we support. We support single precision, FP16, FP11, int8 on all these different frameworks. And we'll fold these scalings in. We move batch normalization to scale shift, other optimizations. More on some of the linear fusing. So batch norm becomes gets decomposed into scale shift, which allows us to move things around. We'll merge the linear operation, or merge the linear operations. We'll fuse mult and adds into multadds, and we will also, so here's an example of things we do. So in the original model, you might do a convolution followed by a batch normalization, followed by a ReLU. When you do batch normalization changes a bit in training, but in normalization it becomes constant. So the first thing we would do is fold the batch normalization into the convolution. And then we realized that most of our devices have this convolution ReLU operation, so we would fold that in. And we go to inference, we're just doing a whole lot less operations. And these are usually agnostic to the hardware you're running on. We'll also cut off parts of the model that you might use for training. We've got command line optimizations for inputs and outputs. This is really useful if you've got a model from somewhere that came from Caffe. You'd like to use our optimizations, but someone has a custom layer on that Caffe at the input or the output. You can change what your input and output is, and then use the old framework to execute what the OpenVINO couldn't do, and still get this. I've also seen this a bit when you're dealing with heterogeneous architectures. You might find that the first half of your model runs well on CPU, and the second half of your model runs well on FPGA. You can take the model and just basically chop it off at the point where it made sense, and say or basically put that onto the Intel hardware, and then use a different software framework for the next piece. Just a little picture of the sort of inputs and outputs. If you've got a prototext on your left, your left. We would run this through Model Optimizer and produce the XML, which you see there, and this is sort of what the inference engine wants to see, as well as a bin file, which would contain all of the weights in binary format. Running it, it's just the Python script, so you would just call the modeloptimizer.py and give it the switches for the where the input model is, where that prototext is, what data type you're using, what scale factor you need, and then where the output directory goes. It looks like this. Here we've called it with all the different switches, and hopefully it says lots of success. So this leaves you off with that XML file and the bin file, which would be the input to the inference engine, and this is going to be the optimized API that Jim was talking about earlier. So in general, you're going to be writing some application up here, and you want to take advantage of all the code optimizations that we've done on the different Intel hardwares. And so we're going to give you an API that makes that sort of transparent. So again, your code doesn't change, but the inference engine has been told that it needs to use either MKLDNN or CLDNN, MOVIDIUS, GNA, or the FPGA plugin. And when you generate the API for this, it'll actually, you'll tell it what order to use these things in. So as you call it, first you're going to initialize the network. We'll talk about that. And then the main loop, you'll do basically frame processing, or you'll be putting your bits of data in bit by bit and taking the interpreted output out of it. So it's easy to include into the application that you're doing. You get a runtime for integrating the inference and application logic. It's called libinferenceengine.so. It'll do all the loading and parsing and everything you need to do there. The plugins allow you to access the MKLDNN, the CLDNN, and the FPGA libraries. So basically finding the right hardware that works well for the network that you've actually got. Because you can do that, again, you're not locked into one piece of hardware. So you can work on several different devices, everything Intel makes. And again, this heterogeneous execution can be triggered independently between loading your networks and setting which binding of layers you want to which hardware. Also, we'll put the pre-processing in the right place. So often the networks want to see things in planar format, and if you're dealing with video, it usually comes in interleaved. So typically this first stage we'll usually do on the CPU, because there's just not enough of it to really justify the FPGA. So we'll restructure those things. And the post-processing, I think I mentioned earlier, we usually do things like softmax on the CPU, as well as drawing of boxes and other things like that as part of SSDs. Calling the inference engine is easy. You'll just have using namespace inference engine, and we've got the different classes that are accessible with that. The inference plugin, NetReader, we'll go through some of these things, blobs, and the executable network. So the first thing we would do is load the plugin. So the member of the inference engine library is plugin dispatcher, and we'll bring in those things. These slides got messed up a little bit. And then here you're going to read in the XML file and the bin file that came out of the model optimizer. We prepare the blobs. So this is just massaging of data, typically done in C, and also setting up an output blob for your outputs to come out of the inference engine. Then you just, from that, create your network from the plugin. You do the inference infer, just executing through there. Now all the stuff between executing on the CPU, executing on the FPGA is handled automatically. And then you just grab your data out of the output blob, and it's accessible in that application. So, this is just everything on one slide of a typical flow. Not many lines of code for getting a lot of bang for your buck. We're going to read the network in, pick the devices, execute the network, and then sorry, just a second. Load the network into the device, then we execute the network and we'll process the output. For batch execution, you can set the batch size. FPGA works really well in low batch, which if you've got low latency applications, if it's part of a solver loop or something, you set that to be quite small. If you're data insensitive, you can set the batch size to be large. Again, we ship a bunch of demos with this to get you guys started, including full applications that are built around FPGAs. And again, this gets back to the customization flow for people who don't like to program in Verilog or VHDL. We've got many different points which you can stay at. So if you want to stay out of the guts completely, you can use the unified API across all the different hardware. If you want to get down into the plugins, that's available. We can customize at the OpenCL level or even at the library level below that. What are the requirements to run it? You just download the toolkit off the web, available free for everyone. The board support packages come with whatever board you've got via, this is we call the Mustang board here, available from IEI, and this is the PAC board, which runs the OPE interface. And so if you've got the hardware, there's a stack associated with the hardware that gives the OpenCL bindings to it, and then you download the toolkit free off the web. So with the OpenCL runtime, you've got that with the hardware and the board support package, and the programmer might possibly be needed, but usually not. When you've got everything installed, you can make sure that your card is seen, diagnose to make sure the card is being read, and ensure that you see this as passed. Then you load one of the pre-configured images. Just with the AOCL program command. Again, all of the walkthroughs are available online, and execute the user application. It's pretty easy. One of the things is we put a performance predictor in there to give you different performance, but in the meantime, the easiest way to do this is just write a script that does all the different AOCL loads to load all these different images, and then just runs them all. Usually applications, you can roll through 7 images in a couple seconds and just figure out which one runs fastest. Using OpenVINO, again, we've talked about these different things, but we can just start with the applications that are in the application directory, copy them to your work directory, and go ahead and run those make files and see how things work. Down here, it's just sort of good to point out that switching different pieces of hardware is as easy as passing different flags into this hetero command. So if you want it to be, when you just list the guys in order here, what it'll do is run a greedy algorithm. So everything it can run in the FPGA, it will, followed by, if it can't run in the FPGA, it'll do a CPU. You can throw GPU in there as well. So that's a summary of just how to use the OpenVINO toolkit. The key takeaway there is all the guts of programming LUTs and arranging data through DSP blocks. All of that is handled for you in those pre-compiled images, and this acts a lot like any other accelerator when you use the OpenVINO toolkit. So definitely be interested in people taking a whack at their own problems that aren't necessarily image classification with OpenVINO, and Jim and I are happy to follow up with anyone who's got some ideas there. All right, lots of different web links. These slides are going to be available on the Dropbox, so you guys can click on these links later. All right, so now we're just going to take a really hard segue into sort of like where FPGAs are going. So before I take this hard segue, any questions left on the OpenVINO toolkit for us? All right, so we've talked a lot about Stratix 10 and Aria 10. Moving into 10 nanometer, we're going to have a new FPGA family. Officially, this will be the very first FPGA family that we've done from soup to nuts under the Intel umbrella. We actually started Stratix 10. Even though it's on the Intel process, we started that when we were pre-acquisition. So what are we doing with this next FPGA? So first off, we're looking for Higher performance compute, we're getting this a lot with the Intel 10 nanometer process technology, which looks quite good in terms of density. We're going to take advantage of our living with the Xeon people to have that coherent Intel accelerator interface and maintain the massive bandwidth and even expand it. We're looking to to have increased integration with more memories and more analog and more logic on chip, and be able to support that from different nodes in the same package, as well as having rapid eASIC development. So if you've got something in an FPGA that needs to go to ASIC, eASIC is a structured ASIC program that makes that a lot easier. And it continues to provide a wealth of tools from the RTL level to what we'll talk about in the next section, which is one API, still supporting C and OpenCL as design entry languages for FPGA. The big headline slide is this will be our second HyperFlex architecture. If you're not really familiar with FPGAs, the easiest way to describe HyperFlex is that we noticed that as you scaled FPGAs to smaller and smaller nodes, the amount of time you spent going through gates began to get smaller and smaller as a percentage, and the amount of time we spent going through routing became bigger and bigger. So what we've done to get Fmaxes back up is we've put basically registers in the routing fabric. And we learned a lot through Stratix 10. It goes faster than the previous architecture, but there's a couple things that had we done the first time through would have gone a lot faster. So those will be in the second generation of HyperFlex architecture. We should get a lot more lift from this inclusion of registers in the routing fabric. We've got 40% higher performance. That's mostly due to the second generation HyperFlex fabric, as well as 10 nanometer being quicker than 14 nanometer. We're also going to see a big power drop by going to 10 nanometers. And changes in the DSP architecture will let us get to 40 teraflops of half precision on the FPGA. We'll support the new memories that are coming out, both the HBMs and the DDR5s, as well as Intel Optane memory, which gives you sort of persistent DRAM, and that can be a big boost to solving a lot of problems. We'll be able to support, as well as PCIe Gen 5, the CXL, the coherent interface for the next generation of Intel chips, all of them, as well as serial transceivers going up to 112 gigabits per second. This is a slide describing the any-to-any heterogeneous 3D integration. What we're saying here is inside of packages with Intel's EMIB interface, that we can insert different transceivers as they come out, different coherent interfaces, and then there's an other. This is a public slide deck, so there's many of the others we'll leave as other for now. If you've got some particular things you're interested in, let's keep talking about that. And one of the things we're excited about is PSG under Intel acquired eASIC, which is a structured ASIC company, which allows us to take things that you expect not to change, harden them into a tile, and add that on die. Not on die, on package. Again, this will be a big point of extending FPGAs going forward. FPGAs sort of lower the cost of entry into new nodes, which have a boost, but once functions are fixed, you can get better efficiency by going first to structured ASICs. So we'll have an automated flow to structured ASIC, which will be relatively cheap and pretty fast compared to going to full ASICs, and we'll also support moving FPGAs all the way into full ASICs on the Intel Foundry, which will give you lowest power and cost per unit. Obviously, it's got a time to market and cost hit for getting there. Again, taking advantage of being part of Intel, we'll have the CXL Compute Express Link, which will give you a coherent link between Xeon, FPGA, and any other Intel technologies developed in this time. They'll all come out together, which is also nice because we know the timing of the Xeons that have CXL, so we'll release our stuff at the same time. We've got some of the best looking transceivers coming out these days for networking applications, so making chips talk to each other. We're supporting up to 112 gig serial transceivers and up to PCI Express Gen 5 on this new chip. We do think this is going to be well, going back to the first part of the presentation, we'll support AI quite well. We've hardened bfloat 16, whoops, I'm supposed to point with this. We've hardened bfloat 16 and FP16. So again, we're getting basically more efficiency across a broader range of data types. And then, still we've got gates to support int 8 through int 2. And we intend this to be very complementary. This puts the FP16 performance up to 40 teraflops on the big parts, and the int 8 performance up to 92 teraflops. Sure. We're also going to be supporting this, again, through our typical design software, which is under everything called Quartus. This takes RTL and makes bit files, as well as OneAPI, which is a new Intel-driven open source language that will be able to support multiple devices. And my next section is on OneAPI, so I'll talk a little bit more about that then. Here are the different series of FPGAs coming out. The F series is what I would just basically call a vanilla FPGA. This is what most of our people who buy parts and stick them on boards are going to want. The next one we're going to do is a FPGA that's built for very high-speed networking, and this is going to have the faster transceivers. And then, about the time that the CXL-equipped Xeons come out, we're going to produce this M series, which is going to have the CXL attached to have coherent attached FPGAs. We hope that to be pretty useful in an HPC world. Some interesting things we can do with this is we'll expect to have very efficient applications into networking via virtualized network functions. And this will give you, more advanced switching and routing, being able to embed encryption in line, just to give you guys some sort of things that, this next generation of FPGAs will be able to do. We're hoping this works well in the data center, primarily by being able to have these FPGAs work seamlessly with all the different types of memory, especially the Intel Optane persistent memory, and also having that coherent memory link. So it'll just make it a lot easier to code and be able to use FPGAs when you can essentially inline instructions and basically have the data flow directly out of the coherent memory into FPGA and get put back there for the Xeon to do the next processing step. We think those will be big in 5G. We just left this in here because, again, it just sort of talks about the ability of the FPGA to do things that FPGAs are really good at, like FEC, encryption, things like that, but also to be able to handle ingest of direct data. Some of the big science applications talk to, very big scanning microscopes or particle accelerators. So if you replaced antenna with, your big scientific instrument, you could use FPGA to do the data conversion, data conditioning, and have that sort of accessible easily, sent to another FPGA to be decrypted or whatever and processed by Xeons in your cluster. So we think Agilex will put us, essentially in a good position to recognize the spatial acceleration going forward. All right, any fun questions on the next generation of FPGAs? Anything we forgot to put in this family that you guys would really like to see? Okay. Lastly, I just want to touch on OneAPI. I was surprised to see that there wasn't another OneAPI in the discussion. At least we tried to comb through the 2 weeks of talks. But OneAPI is beyond a FPGA thing. In fact, it's probably first. It's an Intel thing that allows a single set of source to express, to be executed on all the different hardware that Intel produces. So a single programming model to deliver cross-architecture performance. This slide you actually saw before, and it was originally in this part of the presentation, but we sort of stuck it again in the beginning of the presentation just to sort of lay the foundation of all the different pieces of Intel hardware that we intend that you should be able to access with that single unified source. So yeah, Intel's recognizing that CPU doesn't solve all problems best, but we still want to give you a programming model that addresses all of that seamlessly. So the the concept is you're going to have a single set of one API tools with optimized applications, middleware frameworks, and libraries that allow you to tackle the different pieces of hardware. So if the problems are best executed in a scalar platform, a vector platform, a matrix platform, or a spatial platform, we'll be able to address that. This is the new acronym that we're throwing around a lot, SVMS. This is scalar, vector, matrix, spatial. The basis of this is data parallel C++, which is an emerging standard. We're adding to that the extensions that we need to make this work well across different Intel hardware and working to push them back into the data parallel C++ framework or the standard. Well, there's very few slides on that. So this is actually the last slide I was looking to present. Is there, we did a little start, but I guess we went decently quick. Is there any other questions that we can answer? Marta's disappeared. I guess she doesn't expect us back. Yes?
Is there any sort of time frame for the rollout of one API?
Yeah, so the beta release is work week 40, which Intel, yeah, we speak work weeks. So if January 1 is the start of work week 1, then work forwards, that's somewhere in September. It's coming up pretty quick here.
Yeah, back to my work week mapping.
Yeah.
Later on this year.
You can actually turn it on in Outlook, which is what we all have. But yeah, so it's like late September is the target date for the beta release of that. And the first two pieces of hardware will be CPU and FPGA. You should be able, you'll probably have to contact someone at Intel to do it, but that'll be available on the AI Dev Cloud. So if you'd like to play with it, you can log into the AI Dev Cloud and give that a shot, as well as there's a few different beta engagements, maybe with Argonne, where if you're there, you might have access to that too. Any other thoughts on that? And then, yeah, I guess as more hardware rolls out, we'll roll those into new releases. Yeah.
So what's your thoughts on the Intel FPGA versus other competitors on the market? So pros and cons, strengths and weaknesses.
Yeah, I mean, you're certainly asking someone with a conflict of interest. Yeah, I mean, I think they've got a good product too. Where our strengths have been with including single precision in the DSP blocks by doing hyperflex. That should allow us to get very good Fmaxes. And then I think going forward, you're going to see a lot of advantages that come with living as part of Intel. So if you're talking about this heterogeneous architecture, we've got a very unfair advantage in knowing what the rest of Intel is doing, which our competitors do not. So I think those are some key things. I don't know. Is there anything you like about our competitor's product that you think we should do better? Okay. No, I'm open to constructive criticism. Yep.
Do you expect this to eventually make its way into consumer chips the way GPUs have?
Not really. And this would be the Greg Nash personal take. I think I talked a little bit before about the low volume, high mix. There's a fairly decent static power penalty, and consumer electronics is just very, very power sensitive. So we sort of live in this area where we've talked about this design flow a lot. We live in an area where you really want to have an ASIC that does something that the CPU or GPU doesn't do, but because your volume isn't very high or because you need to actually get to market faster, we're that thing in between that can do just about everything. So if there was sufficient volume to actually justify putting something on an FPGA into every consumer device, then somebody before it gets to the consumer device says, hey, there's going to be 100 million of these. I'm going to go down that path of structured ASIC and build an ASIC and put that in customer. In terms of you just want to work with this thing and you don't want to go to the AI Dev Cloud and you'd like to try developing on this stuff, we do have some very small FPGAs that you can pick up for a couple $100, plug that into the side of your computer and develop on that. So in terms of reducing that barrier of entry to try and program on these things, yeah, we can do that too, but you just get a small FPGA. I don't think we'll ever hit that commodity thing because it's the, there's not that magic super thing that FPGA is best at. And if there was, then someone would just ASICize it. It's kind of a catch-22.
Yeah, and Greg had mentioned, we have acquired a company, eASIC, to help be able to take FPGA and turn it into an ASIC, and it's exactly for those places where FPGA is being used. Now it really makes sense to put it into a very high volume application. And the second that happens, you immediately want to figure out, okay, well, how do I really get rid of all the customizability of my FPGA to make things even more efficient, and you turn it into an ASIC.
Yeah.
So,
Though on the never say never, if you would have asked me 5 years ago if we would, be in broad deployment across data centers, I might have said no then too, and I'd be absolutely wrong today, because we are in broad deployment across some data centers. And those customers value to say that, hey, we're going to deploy this thing and it's going to live in this data center for 5 years, and I don't know the day I deploy it what I need it to do in 5 years. So I still don't see that in laptops, but again, I would have been wrong 5 years ago, so maybe I'll be wrong again. Any other thoughts? Yes.
So the OpenVINO project has really lowered the barrier to entry for these machine learning applications. Are there similar efforts for other applications of the FPGAs?
Yeah, absolutely. We've got partners who support basically doing versions of Apache Spark on FPGA. We think that's going to be quite big. I do think the getting, because very few people actually want to think about their problem on a gate-by-gate level. Basically having people build these frameworks like OpenVINO to make them accessible is how we get to broad appeal. So OpenVINO would be one, supporting Spark is another. I'm on a steering committee where we talk about what next. There's some financial applications that we're going to bring in. Mainly for banks. I don't actually see anyone with dollar signs on their cards here, so I just skip that. And yeah, the big one I want to do is DAL, the Data Analytics Acceleration Library, because as we talk about this sort of space where there's a big suite of Intel accelerators, for the networks we know, these Nirvana products are going to do. I mean, they are ASICs built to do networks. They're going to do a great job. But there's still a lot of, I talk to people, there's a lot of decryption, scaling, indexing of information, and the DAL could help us do that. So I'm looking to do a sort of a survey of what a Pareto of what functions of DAL are the greatest use, and then we might target some of those. If you've got suggestions, I'm definitely interested, but that's how we expect to get to broad things. Other things we've looked at are some the molecular dynamics libraries, looking to fit into some of those, as well as some of the OpenFOAM CFD libraries have been some of the things we've looked at. No committed plans, but if you guys have got some opinions, we read a lot of the academic community's work. So the reason we've looked at CFD and molecular dynamics is a few of you have actually done some test cases and said, hey, these FPGAs can do a pretty good job at this. And so we read those, and then we look at developing them further, or maybe even funding a group to take it all the way into the open source library thing. So yeah, if you've got great ideas, let us know on how to help your peers out and bring things in there. More of these are showing up into clouds, and we hope to have some of the new HPC systems built. Nothing specific, nothing signed, but hopefully, we've got, I think it's definitely public record that Paderborn has got a 64-node FPGA cluster. What's the university in Japan that's got another FPGA cluster? I can forget.
I'm drawing a blank. Right.
Yeah, there's another university in Japan that's built another 64-node cluster with FPGAs. So as people begin to work with these, hopefully these applications will, sort of come out at what makes, what applications are well suited for FPGAs, and we'll move forward with those into libraries. Yes.
I think both you and James mentioned it, but does the FPGA plugin work on third-party FPGAs? Does the library of images?
So yeah, o1.org has a it has the full open source framework for FPGAs. We're certainly not making it easy for you to run our OpenVINO and other people's FPGAs.
Yeah, so
you could.
we've set up OpenVINO with an open API. But in terms of the plugin itself targets just Intel FPGAs. So it's feasible someone else could write a plugin for some other FPGAs, but yeah. Out of the box, the only thing that we have to offer is an open API that anyone can use, and then we built a plugin that knows how to target our FPGAs.
Yeah, for what it's worth, getting really good performance out of this has required like the processing elements. So if you look at the stack, we've got all of this is programmed in OpenCL, but OpenCL can actually, what we call the external functions interface, so it can bring in Verilog and VHDL. And in order to cram the most number of operations we can, we've done some math in some ways that are inexpressible outside of RTL. So it turns out that when you run this, the core convolution actually is written in RTL that is actually tailored to our DSP block. So even were you to target it at someone else's FPGAs, it wouldn't work very well.
And the university in Japan is University of Tsukuba. They've got this 64-node Stratix 10 cluster.
There's some others coming out too, but NDA. I think they'll publish soon, but they like to control that. Thank you very much.
Anything else? Thank you.